Welcome. This is Coach Dorf. In this video, we're going to talk a little bit about the background in Trig. So first of all, when we talk about Trig, one of the things is that it is connected with circles. Let's give a little background about circles. If I go all the way around the circle, that is 360 degrees. Now, in calculus, we can talk about degrees, but we also talk about radians. And 360 degrees is the same thing as 2 pi radians. You may ask, why do we talk about radians? Well, it turns out in calculus that the calculations and the formulas are much nicer if we use radians instead of degrees. So we have to ask the question, how do we change from degrees to radians? Because I expect that most of you are more familiar with degrees than radians. When we're talking about degrees and radians, we're talking about an angle. So if I have a circle here and I'm going to look at an angle. So here's an angle. I'm going to call that angle theta. Theta is a Greek letter, and that equals the degrees of the angle. So in this one, we're going to say theta equals 60 degrees. And the question is, what is 60 degrees in radians? I'm going to use the fact that 360 degrees is equal to 2 pi radians. So we start off with the angle that we're given, 60 degrees here, and I'm going to multiply it by a fraction. And on this fraction, whenever I multiply something by a fraction, as long as the top and the bottom are equal to each other, I don't change the value of the original result I have. So if I multiply a fraction by 2 over 2, it still keeps the original amount equal to what we started with. In this case, I'm going to multiply it by 360 degrees, and I'm going to multiply by a fraction that has 360 degrees and has 2 pi radians on it. One's going to be on the top and one's going to be on the bottom. And I have to ask myself, how do I know which goes on the top and which goes on the bottom? We're starting with degrees and we want to end up with radians. What we want to end up with goes on top. So now let's go multiply this. When I do this, I have 60 degrees times 2 pi radians on the top, and I have 360 degrees on the bottom. Now notice that simplifies to be 1 over 6, and the radians are both on the top and the bottom, so they cancel out. That's why we want the degrees here to be on the bottom if we start with something with degrees, because I still have 2 pi and I have radians on the top, and now I can also reduce the 2 on the top with the 6 on the bottom to get 1 pi on top, 3 on the bottom, and radians. And so I can write that down as pi over 3 radians. So 60 degrees equals pi over 3 radians. All right. Again, the key step here was to multiply the original degrees by a ratio, a fraction that has 2 pi on it and 360 degrees. And because I start with degrees, I want degrees on the bottom and radians on the top, so that when the degrees cancel out, I have radians on the top and I get my answer. Now, we talked about that trig functions are related to circles. They're also related to right triangles. I'm going to call this side A. So this is called a leg, and it's one of the shorter sides, and B is called another leg, it's a shorter side, and the long side here is the hypotenuse. I've got my angle is theta. To do the next step, we're going to need Pythagorean theorem. Pythagorean theorem is one of the most important math theorems. And the Pythagorean theorem says that if I have a right triangle, then in this case, with the diagram I have here, a squared plus b squared equals c squared. It doesn't have to be a, b, and c. It could be other letters there. So what really the main idea is that you take the square of the length of the one leg, and to it you add the square of the length of the second leg. If you add those together, you'll equal the square of the hypotenuse. How do we go from here? We can define some trig functions using this idea of the right triangle. So we're going to define it as following. The cosine of theta is going to be the length of the adjacent side over the length of the hypotenuse. You may ask me, what is the adjacent side? This side, it's a leg, and it's called the adjacent side because it's adjacent to the angle. This side is the hypotenuse because it's the longest side, and this side here is called the opposite side. It's opposite the angle theta. It's farthest away from the angle theta. Going back here, we have cosine of theta equals the adjacent side over the hypotenuse. And in my original diagram, remember that we call this side B and this side C, where there's my right angle. So the adjacent over the hypotenuse in this case would be the same as A over C. And that is what cosine of theta equals. Likewise, we can do sine of theta, and that is the opposite over the hypotenuse. And in this case, it's going to be B over C. And finally, we can do the tangent of theta, which is opposite over adjacent, and that's going to be B over A. And so that's one way we can define these three trig functions: cosine, sine, and theta. And just for clarity's sake, cosine is written this way, but we also then talk about the cosine of an angle, and we just write it COS. The sine is written this way, and we write it as sine and theta. It doesn't mean sin, that's the abbreviation we use for it. Then the degrees cancel out. So let's do an example here. If the sine of theta is 3/5, and I'm going to say theta is between 0 and pi over 2, what is cosine theta? Now, first of all, you may say, why do I have that theta between 0 and pi over 2? These are radians, so 0 radians, and we have pi over 2 radians. 0 radians is the same as 0 degrees. What about pi over 2 radians? We can look at this just like we did before. We're going to multiply this by a fraction that's going to involve 360 degrees and 2 pi radians. And what goes on top, what goes on bottom? I want to end up with degrees, so I'm going to put the 360 degrees on top, the 2 pi radians on the bottom. Then I have pi radians times 360 degrees all on the top, 2 times 2 pi radians on the bottom. And now we can start canceling things out. The radians cancel each other out. The pi's cancel each other out. And so then I have 360 degrees over 2 times 2, which is 4, which reduces to 90 degrees. So pi over 2 radians is the same as 90 degrees. So here we are saying that the angle theta is between 0 degrees and 90 degrees. In the example we did here, we ended up with degrees because we put the 360 degrees on the top. Now let's continue with this problem. We were given that sine of theta is 3/5. Let's look at this right triangle here. Here's my angle theta, and I've got the sides A, B, and C. And I know the sine of theta is the opposite over the hypotenuse, which is B over C. And I know that sine of theta is 3/5 because that was what was given to me. We can then let, in our triangle, we can let side B equal to be 3 and side C equal to 5, because we have this equal to this. These are equal to each other. So then I could ask myself, what is A? And here then I would use Pythagorean theorem, which would say, because I have a right triangle, I know that A squared plus 3 squared is going to equal 5 squared. So that's A squared plus 9 equals 25, or A squared equals 16. And now if it says A squared equals 16, that means what number times itself equals 16? In that case, I'm going to get 4. Some of you may notice that I could also get -4, because -4 times -4 is 16. But A is a length. We're not dealing with negative lengths, so A is going to be +4. And we're going to use this here, A equals 4. Our original problem is to figure out what cosine is. So what is the cosine? Cosine of theta is going to be adjacent over hypotenuse. And I look at this, my adjacent is 4, my hypotenuse is 5, and so I get that cosine of theta is 4/5. Otherwise, if I wanted to do this, I could also figure out what the tangent of theta is. Tangent is opposite over adjacent, and the opposite side was 3, and the adjacent side was 4, and so tangent of theta equals 3/4. Now there's another way we can think about trig functions. So we've talked about trig functions, we've talked about circles, we've talked about right triangles. So let's go back to circles and combine these two ideas of circles and right triangles. This is my x-axis. So think of it as a graph. Here's my y-axis. And inside my circle, now since I have my x-axis and my y-axis, this point on the circle is an x value, comma, y value. Any point on the circle would be that. This point here is the origin, so it's 0, 0. And this creates a triangle. I can create a triangle, a right triangle, by using this amount here. So let's bring that right triangle over here. And if this circle that I start with is, so we say a circle centered at the origin, so that means it's at 0, 0, and radius is 1. That's the equation of a circle centered at the origin of radius 1. If it was a different radius, let's say radius was 2, the equation would be x squared plus y squared equals 2 squared, or x squared plus y squared equals 4. Going back to my triangle here on the right side, my right triangle, here's my angle theta, here's my point x comma y, and this is my point 0. This is the hypotenuse, and because it's a circle of radius 1, this has length 1. And because this point here on the top part of the triangle is x comma y, this length is x, the length on the bottom is x, and the length on going up, the height, is y. I could say the cosine of theta, which is the adjacent over the hypotenuse, equals x over 1, because the adjacent is x, it has length x, and the hypotenuse has length y, and so that equals x. So the x value equals the cosine of theta. Sine of theta is opposite over hypotenuse, which is y is the opposite side, hypotenuse is 1, and so we get y. So the y value equals the sine of theta. So that's how we can connect circles with right triangles, and that leads us to then the trig functions. Let me give you a little bit more background on one other aspect. If I have an axis, so everything in this part here is known as the first quadrant, and over here this is the second quadrant. This one, this orange side, is the third quadrant, and the green side here, this is the fourth quadrant. Now let's look at some angles in a circle in the first quadrant. So I'm going to draw my axis again, draw a circle, and now we're going to just look at some angles in the first quadrant. This angle here is 30 degrees, and we could figure out that this is the same as pi over 6 radians. That's a very common angle that we'll use there. Purple, there's 30 degrees. This is about 45 degrees, which turns out to be pi over 4 radians. And I can compute that 45 degrees is pi over 4 radians by just using that technique that we showed at the very beginning. This is 60 degrees, which it turns out to be pi over 3 radians. We showed at the very beginning how to do that one. If I go all the way straight up, this is 90 degrees, or pi over 2 radians. The angles 30 degrees, 45 degrees, and 60 degrees, or in calculus as we would say pi over 6, pi over 4, and pi over 3 are in the first quadrant, right? 90 degrees, or pi over 2 radians, is on the border of it. If I did this one right here, that would be 0 degrees or 0 radians. 0 degrees or 0 radians and pi over 2 radians are the borders of the first quadrant, and pi over 6, pi over 4, and pi over 3 are the main angles in the first quadrant. Those are the ones that we will be using. What are the sine and cosine values in the first quadrant and its boundaries? So let's make a little table. So here's 0 radians, here is pi over 6 radians, here is pi over 4 radians, here's pi over 3 radians, and here's pi over 2 radians. All right, and I'm going to let my angle be x. And what I want to look at are the sine and cosine values. So cosine of x, sine of x. All right, for the cosine of x, if x, the angle is 0, this is going to be square root of 4 over 2. If you memorize that and you follow this pattern, then we'll be able to figure out the rest. And this is a really cool pattern. This is what math is about often, is patterns. So if I do the angle 0, I get square root of 4 over 2. If I go to the next one, pi over 6, I get square root of 3 over 2. If I go to the next one, it's square root of 2 over 2. The next one is square root of 1 over 2. And the last one is square root of 0 over 2. Nice pattern. We go square root of 4, square root of 3, square root of 2, square root of 1, square root of 0. And then the bottom is always the same. Now, what we should do next is we don't leave these always in this form. We simplify them if we can. So what is the square root of 4 over 2? Well, square root of 4 is 2, so I have 2 over 2, which then reduces to 1. So that's the more common representation for the cosine of 0. It's equal to 1. Square root of 3 over 2 doesn't simplify, so we just leave it like it is. Square root of 2 doesn't simplify, so we leave that one like it is. Square root of 1 does simplify. What's the square root of 1? It's 1. So now I have 1 over 2, and that's that answer. And the last one, square root of 0, that's the same as 0. So I get 0 over 2, or 0. That's really cool, I think, that you have this pattern that works for these angles. All right, what about sine of x, the sine of these angles? Well, it's exactly the same thing, but the order is switched. So we start with the square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. And if I simplify it, I get 0, 1/2. I keep square root of 2 over 2, keep square root of 3 over 2, and the last one I get 1. I think that's really cool. I hope if you're watching this that you're just like saying, wow, isn't math so cool? Okay, what do we do if we have an angle in a different quadrant? So we know what to do if we're in the first quadrant. What do we do if we're in a different quadrant? So let's look at the different quadrants again. So this is the first quadrant here. And remember that this is the x-axis and this is the y-axis. If I just put some markers here, if I take a point, like this is 1, 2, this is 1, -1, -2, -1, -2. If I were to take a point like this one, that would be the value 2, 1. Notice here that what's always true in the first quadrant is that x is greater than 0 and y is greater than 0, right? The point 2, 1, I don't have any negatives. If I go to the second quadrant and I take a point here, let's see, that point's going to be -2, 1. So what's true here in the second quadrant? X is less than 0, y is greater than 0. If I'm in the third quadrant, let's say we take this point here, that looks to be like -1, -2. So what's true? X is less than 0 and y is less than 0. They're both less than 0. And in the last one, the fourth quadrant, if I take this point here, this is 2, -2, I have x is greater than 0 and y is less than 0. This is important to help us because we know that the x value is equal to cosine theta and the y value is equal to the sine of theta. So we'll use both of those to determine the sine and cosine values for angles that are in different quadrants besides the first quadrant. So if it's in the second quadrant or third quadrant or something like that. So let's look at a specific example. What is the cosine of 2 pi over 3? So the first thing I need to do is ask what quadrant is 2 pi over 3? 2 pi over 3, what of the original angles that we talked about in the first quadrant is that like? In other words, what one has the same denominator? We had 0 radians, and then we had pi over 6, we had pi over 4, we had pi over 3, and we had pi over 2. And those were 0 and pi over 2 were on the boundaries, and pi over 6, pi over 4, and pi over 3 were inside the first quadrant. 2 pi over 3 is going to be similar to the one of pi over 3 because they both have a 3 in the denominator. That's what's important. Pi over 3 is right about here. If I look at 2 pi over 3, it is over here. What becomes important here is to notice that if I draw my triangles in here like that, what are the corresponding x values and y values? Well, here y value for pi over 3 is the same as the y value for 2 pi over 3 because the y is going up, they're both positive. And if I look in the second quadrant, going back to what we did before, in the second quadrant and the first quadrant, y is always positive. So those are positive y values. The y value is the sine. So let's just look at the sine the sine of pi over 3 is going to equal the sine of 2 pi over 3. They both have the same height, right? There's the height of pi over 3, there's the height of 2 pi over 3. They're exactly the same. What about the cosine of pi over 3? Well, that is the base here. That x value there, and then here, it has the same length for, if I look at the 2 pi over 3 value, the x value has the same length. Going back here, if I look at in the first quadrant, x is positive, but in the second quadrant, x is negative. So they're going to be negatives of each other. So the cosine of pi over 3 equals the negative of the cosine of 2 pi over 3. That comes because here is this x value here is the cosine of pi over 3, and this red line I'm drawing in right now is the cosine of 2 pi over 3, but it is in the second quadrant, so it's going to be a negative value. So how does that help us? Well, that means if we're trying to figure out what the cosine of 2 pi over 3 is, it's going to equal the negative of the cosine of pi over 3. And what is the cosine of pi over 3? Well, if I go back to my chart here, the cosine of pi over 3 is a half, so I'm going to get a half here with a negative sign. So the cosine of 2 pi over 3 equals negative a half. All right. See how that's related to the cosine? Remember, the cosine of pi over 3 was a half. The cosine of 2 pi over 3 is negative a half. What about if I did the sine of 2 pi over 3? What about that? Well, the sine of 2 pi over 3 is the same thing as the sine of pi over 3, because it's the y value, and when we go to the y values, they're both above the x-axis, so they're both positive. So they have the same sign. And what is the sine of pi over 3? Well, if I go back here, the sine of pi over 3 is square root of 3 over 2. So this is square root of 3 over 2. So the sine of 2 pi over 3 equals square root of 3 over 2, which is the same thing as sine pi over 3. Okay, I'm going to stop there and continue this with the next video. Thank you.